It'd be amazing if we could talk about the observational aspect of this, the tools of observation. So, what telescopes have you used? Do you use? And what does the data look like? And I think I've read a few interesting stories about the actual process of day-to-day observation. A bunch of probably late nights.
Well, yeah, astronomers are doing it all night long, so we
Well, yeah,
have lots of late nights.
Can you explain the all night long aspect of it?
Well, let me start by saying I mostly these days use the Magellan telescopes in Chile. They are 6.5 meter telescope, which means the mirror diameter is 6.5 meter. That's not the largest that is out there, but it's among the largest. And I use a spectrograph because I'm a spectroscopist. I don't take pictures. And that particular spectrograph at that telescope is actually unusually efficient. So it kind of makes up for the fact that the mirror isn't as large in, let's say, the 8-meter telescopes from the Europeans or so. So I'm very happy with that.
Efficiency meaning?
How many photons get collected sort of per time unit?
Sure.
Because that's always the limiting factor. Prior to the pandemic, we would travel to Chile to do our observations. Those telescopes that's the last observatory where people were sort of supposed to travel there and take their own observations. Most other observatories basically have staff there by now who take the observations for you.
So there's the scientists are specifying where to point the telescope and sitting there and collecting the data, making sure the data is collected well, the cleaning of the data, the offloading of the data, all that kind of stuff.
Yeah, so it's mostly done for them.
Yeah.
Obviously, that's super convenient, but it also takes away a central part of what the work of an astronomer is, which is data collection. Right? We don't have an experiment in the basement where we can go day and night or whenever we please and ask a certain question of the apparatus, right? Let's turn this knob and see what happens. Let's turn that knob and see what happens. No, we only have one experiment, which is the universe. And what we see is what we get. And I think it's so important to take an active role in that. So I really loved going to the observatory. I've taken many students there over the years to teach them and to just show them what it means to be an astronomer, because you go to these remote mountaintops and it's such a magical environment, and you wait there, for the sun to go down, and then you get ready and you look outside, and it's such a serene environment. It's a little bit out of this world.
You're sitting there, so the sun goes down, it's evening, late evening. And what does it look like? What are some of the most magical experiences of that process?
Well, when you're on top of a mountain, climbers, I guess, get to see that probably. Otherwise, it's very calm, and the colors are so beautiful. And I always become much calmer when I'm there. Because I'm just there for one purpose only, and that's data collection. I can say no to my emails. I can say no to everything else because I'm observing. So there's literally less distractions because, you're just there to do one thing.
And also the emails somehow seem less significant.
Yeah. It's just you can afford to focus on just one thing. And it just kind of does something to you. It's a little hard to describe, but if you then fast forward, maybe I can speak a little bit about that. I have done a lot of astrophotography there as well. So, and I observing faint dwarf galaxy stars, these are like 45 minutes, 55-minute exposures. So you actually have a lot of time. So I would run outside and just lay on the ground under the southern Milky Way, beautiful, right up, there. And I would just lay there like the snow angel, and just stare up there and just kind of let my thoughts sort of pass through my brain, and just like I'm one of it, right? We talked about this in the beginning. This is when I personally have the feeling that I'm a part of it. I belong here, rather than feeling kind of small. Yes, I'm small, but there are many other small things, and lots of small things make one big whole.
And
right?
we're part of that big whole.
And
so that's looking at the inner spirals of
yes,
the Milky Way galaxy.
And just this dark sky with the bright stars. And I have described this in my book years ago. If the Milky Way is all bright above you, you don't need a moon or anything. You can walk in the starlight and you will find your way. Mm. There are no trees there for safety reasons, but you wouldn't even run into a tree, right? I mean, you can almost see the shadow, from the starlight, because it's such a dark sight and the stars are so bright. And these are kind of moments that kind of change you a little bit. And
you see the unity of it all.
Yeah. And it's just you and nature, and, with modern civilization and all of that, I think we often try a little bit too hard to be removed from nature, to be independent of it and figuring it all out. But at the end of the day, we're just a part of it, and that really helps me to remember that we're one and the same.
Well, that fills me with hope that, because I tend to think of us humans as in the very early days of whatever the heck we are. And so that makes me think thousands, tens of thousands, hundreds of thousands of years from now, that we'll be whatever we become, we'll be traveling out there to explore more and more and more.
Yeah.
So what you're doing is the early days of exploration with the tools we have.
Yes, the early seafarers looking at the sky for navigation.
Coming up with different theories of what's on the other side, that the Earth, starting to gain an intuition that the Earth may be round. And then we might be able to navigate all the way around to get to the financial benefits of getting spices from India, whatever the reason, whatever the grant funding process is all about. But ultimately, it actually results in a deep understanding of the mystery that's all around us. And I mean, it's just to travel out there. I mean, to me, the discovery of life in the solar system, I really hope to see that in my lifetime. Some kind of life, bacteria, something, maybe dead, because that means there's life everywhere. And that's just the kind of stuff that might be out there. All the different environmental conditions, chemically speaking, that are out there. And it just seems like when you look on Earth, life finds a way to survive, to thrive in whatever conditions. And so maybe that process just kind of humbles you, and is super exciting to know that there is life out there of different forms. And of course, that raises the question of what is life even? We tend to have a very human-centric perspective of what is a living organism and what is intelligence and all this kinds of stuff. And all the work in artificial intelligence now is starting to challenge our ideas of what makes human beings special. And I think we're doing that through all kinds of ways. And I think your work in some part doing that as well. Like the unity you feel is realizing we're part of this big mechanism of nature, whatever that is, that's creating all kinds of cool stuff, from the humble, pristine origins to today. So what is, if you could just kind of linger on the process of the data, what does the data look like? And how does the raw data lead to a discovery of an ancient star?
Well, as a spectroscopist, we have to, I guess, talk for a brief moment about what a spectrum is.
Yes.
Everyone, I hope, has seen a rainbow in the sky. That is basically what we're doing. We don't send the starlight through a raindrop that then gets bounced around and splits up the light into the rainbow colors. We do it with a spectrograph, so basically a prism. So we send the starlight through a prism of sorts, and that splits it up, and then we record exactly that. So it's a little 2D picture, actually, of a spectrum. Now, it's not going to look colorful. It's just black and white. Different colors have, of course, different energies. That's what we record. More specifically, we record it as wavelengths. So wavelengths and frequency and energy is all the same at the end of the day.
Mm-hmm.
we process that little image in the sense that we do a crosscut and then sum up a few columns so that we get all the data that we recorded. And what we see is it's a bit funny to describe just with words, but a wiggly line with lots of dips. So the 2D processed spectrum, we call it continuum. So it's just a flat line, basically, and then there are dips. So the interesting things are the dips. If you think back of the rainbow, what we actually see in our stars is not just a rainbow, but it would be a rainbow with lots of black lines in it, which means certain little pieces of color have been eaten away by a certain amount. And so we can no longer see it as well or not at all. Why is that happening? So if we come back to our stars, what we're observing the stellar surface. We can actually never peer with our telescopes inside. We only ever can go after the surface. And the surface the surface layer contains different kinds of elements. Every one of those types of atoms, so elements are just different types of atoms, they absorb different photons that are coming from the hot core where the fusion is occurring. And so that means that if you're the observer, with a spectrograph or without, you will see the starlight, but certain frequencies, certain energies of that light will have been absorbed by all the different atoms in the gas. So you see less of them. And so those are the dips. And the strength of the dips tell us, which element was it and how much of that element was or is in the star. So we have many, many, many dips. The solar spectrum, for reference, all the dips are overlapping because the abundance of all the elements is so high. It's actually a very complicated spectrum. My spectra really look like a straight line, and then there's a dip here, and then you have the straight line again. There's a dip there. The sun doesn't have straight lines. I mean, it's just all absorbed in some form or another. But the old stars have so little of all the elements that there are only occasionally these dips that then indicate, okay, that one at that wavelength was iron, and here we have carbon, and there's magnesium and sodium, and there's a little strontium line here. So we have a much easier way to map out this barcode that the spectrum, pretty much is at the end of the day, and to then measure the strength of these, we call it absorption lines, to then calculate with existing codes that mimic the physics of the stellar atmospheres, like how much was absorbed, how many, what kind of elements were present in the stellar atmosphere. And so this is how we get to our abundance measurements, and then altogether that gives us the chemical composition and that particular signature in that star.
If you do you ever look at like the raw spectrograph and the absorption line, and are able to intuit some interesting non-standard outlier kind of patterns? Or does this have to do heavy amount of processing?
We actually process it's fairly straightforward to do our processing. We do it at the telescope. So I often take a shorter exposure first, let's say 10 or 15 minutes. So mostly when I do discovery work, we would just take a quick look spectrum, then we process it while we observe the next star. Then we take a quick look. We have what I call the summary plot. It's a collection of little areas in the spectrum that have the key positions, the positions of the key elements in it. And it's kind of like reading the tea leaves. I have stared at so many spectra. I just need to know, I just need to see our summary plot, and I can tell you exactly what the numbers are going to be.
And also to tell if it's going to be promising to look at further.
Exactly. And so that's it. Thumbs up, thumbs down. Are you worth my time or not? In most cases, it's not, or it's good enough. We can do a basic analysis, maybe publish this as part of a larger sample, just so, we output that we have observed the star and their basic nature. That's an important part to publish as well. I had a run. So now we do remote observing. I do all of this now from my home, from my living room, all night long. And I often work with colleagues. So we do it over Zoom and we process the data. We look at it, same thing still. And we just found a star that had a very low iron abundance. And then we decided, okay, that looks interesting. We're just going to keep exposing. So we took more data on it on the spot and we're writing up the paper right now.
How do you know where to point the telescope?
It's not random. There's a lot of work that goes into that. I began my career by trying to answer that question, as in like doing the search process. That's why I called my book that I've written some time ago, Searching for the Oldest Stars, because searching is one thing, it's very time consuming. And then on top of that, not everyone finds, right? And I often don't find, but I keep searching because, our techniques have established that, yes, we can do it if we're just patient enough and keep going, because it's a numbers game. And that's often the case in science. And that's something that not enough is talked about, how tedious it is and how long it takes to get to that one discovery, right? That moves the field further.
And how difficult it is to believe that there's a thing to be discovered.
Yes. If we have the saying, I learned this, I think, from my supervisor. 1 star is a discovery, 2 is a sample, and 3 is a population. So as soon as you found 3 of roughly the same kind, you're done. But you need to get there.
Yeah. Probably the first is the hardest, right?
Yes. But it kind of remains really hard. But the thing is, then at past 3, many of us are, okay, we solved that problem. We've shown it 3 times, so we can do it. That's a thing, right? That's a population. 3 iron deficient stars, let's say, right? That's one puzzle piece. Now we can move on to the next thing.
That's an indicator that there's many more of them,
yes.
potentially.
Yes. So to cut a long story short about the searching, we started early on with what's called low resolution spectroscopy of many stars. So, for example, my thesis work almost 20 years ago was piggybacking off a quasar survey that had collected. So quasars are basically giant supermassive black holes that are really far away. So you only see one big bright light point. So it looks like a star, but it's actually just a giant supermassive black hole that outshines its own galaxy. And people had been trying to study those, and they had taken little spectra of all things in the sky. And it turns out, you can fish out the actual stars from that and look for certain signatures that might indicate low metallicity stars, so stars with low abundances. And so it was painstaking work to then take medium resolution spectroscopy to get a little bit more information and to use approximations and to kind of get candidates that we can then eventually take to the big glass like Magellan to get a high resolution spectrum. So we really see the dips of all the individual elements that then give us the final answer. Is it yay or nay? These days, with another grad student, I developed a new technique to use images actually of all the stars in the sky taken with very narrow filters. So it's like you're wearing very specific glasses that only let so much light through. And so we can do similar things through having several narrow band filters, what we call it, to fish out things that have, no absorption over here. So just the straight line, and then a little dip here. So a little something there. And that has proven fairly successful in recent years.
So looking at a broader regions of space.
That's right, because these stars are a little bit like the needle in the haystack, right? There are not that many left over, and certainly the galaxy has made plenty of stars in between. We need to comb through all of those to get to the goods. So we always start with millions and then work our way down, and in the end we have like 3 good candidates.
I wonder how those ancient stars feel that they were noticed. They probably know that nobody pays attention.
Well,
no, I'm just kidding.
We're all special, right? So are the stars.
It's good. It's inspiring, even if you're the outcast. in your pristine nature, you still might nevertheless be noticed. I'm hoping the same about humans if somebody's observing us. Is there something else you could say that's about the challenges of this kind of high precision measurement that you're doing? So this kind of collection of data, trying to kind of pull out the signal from the noise out there.
Well, that's literally what we're doing in multiple ways, actually. So we're trying to find the needle in the haystack, and then we find something, and then it turns out it's just a little bit too faint to actually get the kind of data quality on it that we would like, or that would be warranted given the potential of the star, right?
Mm-hmm.
It's like, ugh.
So there's always noise. There's
Yeah.
always a little bit of noise, and you have to try to say like, how special is this when you're looking at the absorption line?
Yeah.
How?
So the most iron poor stars, their iron lines are so tiny that they're literally, almost in the noise. So you need incredibly good data to make detections. And the funny thing is, we're looking for the nothingness of let's say, the iron lines, but then we don't want nothing, because if there's nothing in the spectrum, we can't measure anything. We can only get an upper limit. But we'd really like a measurement. So we are looking for the last little bit that you could possibly detect. And that's the strong function of the brightness of the star, because the telescopes have the size that they do. That's not going to change for a while. Hopefully, eventually it will, but it's going to be at least 10 years out. And so, yes, we're often literally stuck in the noise because we can't make the measurement. So actually, the record holder for the most iron poor star only has an upper limit. We can't get enough data on this to actually pinpoint a measurement, to then take it to our theory colleagues and say, like, give me this little iron out of your first star. So it's a bit frustrating, but also super exciting at the same time.
So let's go to both sides of that spectrum. What's like the most exciting discovery to you personally? Where is there a moment you remember that you saw a piece of data and your heart skipped a bit?
Yeah, of course.
Is it HE 1327?
That was definitely one of those moments. I wasn't actually present at the telescope, but we were sent the data immediately from our colleague. And we just looked at it and our eyes got really wide and was like, oh my God, is this really what we think it is? So we had to run some numbers, and it was. And these are magical little moments. The thing is, often we have false positives.
Yeah.
And so there's always this kind of period, and often it's I don't know, 10, 15 minutes where you need to make some tests to kind of make the decision. Is this really something I should keep observing now? Is this really as good as I think? Or am I being fooled by something, right? So actually, if you take a spectrum of a white dwarf is the leftover core of a star like the sun that has gone extinct. And white dwarfs have lost all their outer atmosphere, so it's just the hydrogen-helium core. So they look like a metal poor star because there's only hydrogen-helium left, right? But the hydrogen lines that you can see in the spectrum of our stars and of the white dwarfs are a little bit wider than normal. So you need to have a good eye just to check, does this look a little bit wider than us? Is this a white dwarf who's fooling me here, right?
Yeah.
And so it's like this moment, it's like, oh my God.
It's just minutes of nervousness.
Yes. And sometimes, it's a dud, and sometimes it's not.
What's been a big that you remember heartbreak, like a painful low point? Is it all leading up to the first? Is it all about HE 1327 again? Just the leading up to it, or has there been like has there been like low points in this search?
That's a good question. I mean, it starts with mundane things, as in like you won your telescope time, you traveled there, and the weather is completely cloudy, it rains, and you had 3 nights, which is a lot, and you go home empty-handed. So that's definitely a low point. Probably not what you were thinking of, but there is a certain occupational hazard to it.
Which requires a kind of resilience and a patience.
Yeah, and you just got to learn to live with it. Coming back to Reticulum 2, actually, that little dwarf galaxy, that was a run that we had, and the weather was incredibly bad. And I had sent my student there, And I was at home, and he calls me at 2 a.m. and he was like, Anna, I think I observed the wrong star. I'm so sorry. There is this line there, this europium line, and it looks like a metal-rich star.
Yeah.
And I was like, it's cool.
Yeah.
We all make mistakes.
Yeah.
Send me the data. Send me that summary plot.
Mm-hmm.
And so I look at it, I was like super tired. It's like, I can't really tell. It doesn't look wrong, but I can't tell you right now that it's right either. So why don't you go to the next target?
Mm-hmm.
And he calls me back an hour later. Anna, it looks just the same.
Yeah.
What am I supposed to do? And then I joked, well, maybe we found an R-process galaxy. Let's go to the next one. Yeah. And the weather was degrading. And so to cut a long story short, we had to come. So he was observing the right stars. Mm-hmm. It was an R-process galaxy, the first one we had ever discovered, mm-hmm. totally unpredicted. We had no idea that this was a thing. I mean, of course, we thought that, such a thing might possibly exist, mm-hmm. because why not, mm-hmm. right? Neutron star mergers happen somewhere. Mm-hmm. Crazy supernovae probably too, but we were not prepared in that moment to find this thing. And in the end, the weather was getting worse and worse, and we wanted to see how many R-process stars are in this galaxy. So we managed by a hairline to observe the 9 brightest stars, but the data quality was atrocious.
And the weather affects the data quality.
Yes, absolutely, because these were really faint stars. And so we were really lucky by making a very tight strategy of getting the absolute bare minimum for all the stars, so we could at least take a very crude look. Is it a yay or is it a nay? We couldn't even say yes or no, just to get an idea, because we needed to know. Why was that important? Because we could only observe this system again 9 months later.
So there's always a window of observation.
Yes, it was setting. This was our chance, and it was going away with the clouds,
That was super high stakes.
But we just made it. Like, really, it was almost impossible, and it was just the thing is, this is such a serendipitous moment. In a serendipitous moment, the enhancement of these heavy elements was so strong that even in this really crappy data, we could still see the enhancement, mm-hmm. right? The absorption was so strong that it stuck out of the noise. If that enhancement wouldn't have been as strong, we would not have been able to say anything, because we wouldn't have been able to tell. Mm-hmm. But because it was so extreme, it lent us a hand, despite the weather and all, to say, like, yes, this is it. So that was quite the night.
Luck. I mean, a lot of this is just luck. So that was the first R-process galaxy discovered.
Yes. I didn't sleep all that much then.
Do you have hope? Are you excited about James Webb Space Telescope and other telescopes in the future that increase the resolution and the precision of what can be detected out there?
Absolutely. JWST is fantastic already. I am not planning to use it personally, although I think I'm on 1 or 2 observing proposals, actually, because similar to what we already spoke about, we're interested in the same thing. We're just kind of looking at different sides of the fence, mm-hmm. right? I have my old surviving stars, and I concoct these little stories about what the earliest galaxies may have looked like, what the objects were that contributed, energy and elements and all these things. And my JWST colleagues, they try to detect some of these earliest photons from these earliest systems to look at the energetics and other things. What was there, how many, these kinds of things, right? So together we're trying to explore this first billion years, but we do it in very complementary ways. And so I'm very excited to see what they can come up with and how that helps me to inform my stories better and more comprehensively.
What do you think is the future of the field of stellar archaeology? How much can we? Maybe what are the limits of our understanding of this first billion years of our universe?
Well, obviously, lots of limitations in the sense that I always say, I have a metal poor star for any of your questions because there are so many different kinds out there. And we still find new patterns sometimes, right? And there needs to be an explanation. The question is it ultimately just one quirky star? Or is it two? Or is it three, right? Is it a sample? Is it a
Right.
population? So we haven't concluded that kind of work yet.
So every metal poor star is a kind of data point that you can use to improve the quality of your model of how is the evolution of the early universe.
Yes. And I would say we've made huge progress over the last 20 years. When I joined that field, it was in its infancy. And there was this serendipitous discovery of that first, second generation star. And we have filled in the canvas a great deal since then. And this is what I have greatly enjoyed about doing so, because there was so much discovery potential. And it's been dying down a little bit because of all the progress. It's on the up and coming again because there's so many large spectroscopic surveys in the works now that will just provide a different level of data that we haven't had before. I'm sort of these older generation. I have only very few colleagues. I work in small teams and I observe every single star myself. That, whatever I can, I do myself. I don't generally take other people's data, at least certainly not in the end stage. And I'm not a big data kind of person, although we all headed that way. I certainly use data from the Gaia astrometric satellite for the kinematics, for example. But that's personally a new thing for me to use sort of big sky surveys that are available. So it's still very sort of hand-grown field, where we do our individual observations. I have enjoyed that a lot, but that's about to change.
So one star at a time.
Yes.
I mean, there's power to that, to build up intuition of the early universe by looking one star at a time.
Yeah. And this is how you can really drill down on the questions that you have, right? Because you control what data you get. Otherwise, you have the data that you have, right? You get what you get and you don't get upset. I don't like that. I'm a little bit snobby. I really like to formulate my questions, go to the telescope, and then come what may, I will try to get it.
And also develop the intuition of where the data can be relied upon and where it can't, and all the different quirks of the data and all that kind of stuff.
Yeah.
Sometimes a lot is lost in the aggregation of the noisy data.
Yeah. And there's always the danger if you have someone else's data that you just don't really understand the limitations, completeness things, how certain things were set up, and you get out what you put in. So I'm really particular about that, and it certainly paid off for me. That's one of the main notions that I try to teach in my classes and to my students, that you need to be able to formulate your question really well, because otherwise you're going to get an answer to a different question, but you won't notice that that the goalpost has shifted in the meantime, right? So your interpretation can only be as good as the question. If you need to change your question, that's cool. Do it. But then, it needs to pair up with your interpretation again. And so really being in the know about every step of what happens, that leads to quality results, I think. That's why I have sometimes little trouble with sort of big data and statistical analysis. Yes, on average, that's true. I'm not debating that. But I'm the kind of person, I like to look at the outliers, so not the bulk, but the special ones.
Yeah.
And they just need to be treated in a different way. And there needs to be an acknowledgement of that, different ways for different things.
So big data can look at divorce rates. And perhaps you and I are more interested in the individual love stories.
Yes. that works for me.
I don't know if it's possible to say, but what do you think is the big discoveries that are waiting? Is it on the different dynamics of the yield, the common narrative, the common story of how some of these metal poor stars are formed? Where are the discoveries in this field that you think will come?
I think the individual discoveries are we've made most of those, certainly through individual stars. Finding yet another second generation star is incredibly important for me, but isn't really going to move the needle. Finding 50 of them or 100 of them, that would move the needle, but that's an order or two magnitudes up. And new search techniques and new surveys may enable that, but would you still call that a discovery?
Sure.
Right?
So that's just a scale. That's a scale thing.
Yes. So I think about it more like literally of the puzzle. Let's say you have a 1,000-piece puzzle and you have 900 pieces in there. If you're a person like me, I want to get to the last ones. I'm not going to leave it. It's like, okay, I see broadly what this is going to look like, right? I'm done now. No, I want to get to the last one. So is the picture globally going to change? No. Are we going to figure out all the details and how it really works? Yes, right?
So really carefully
Getting
detail map
into
out
it.
the ancient stars of our universe.
Yeah, because I think that's what many of us scientists are a little bit detailed obsessed. But I think that's our job too, right? To really kind of make it airtight, to really walk away saying, I fully understand this. Not just broadly, but I really know. We really know now. And so more and more of that is going to happen. And so I think this is probably true across astronomy. These individual 10 sigma discoveries become less and less. If they were easy, we would have made them already, right? Which means we have made many of them. But really filling in the details is the next sort of level of discovery. Maybe we need to find a new word for that. The hopes and expectations that go along with the word discovery are so enormous. We may not always be able to live up to that. But it doesn't mean that we're not finding out new things. It's just a different kind of quality because the questions have shifted. You close one door, suddenly there are 10 new open doors that we want to explore and march through. And that's finding these last puzzle pieces here and there that really make it airtight.
And so there's a lot of value and a lot of power and beauty to the discovery in the big picture of our universe and in the details.
Yes.
So both are
we
really
need both.
important.
Absolutely.